I'm Alex Mazurski from the University of Chicago, and today I'm excited to share our work, Power on Touch. So let me show an interaction to illustrate what I mean by power on touch. This user types his code into the keypad and unlocks this locker. But this isn't an ordinary locker. You see, we've removed the batteries from the keypad, and yet it can still turn on and can even actuate that unlocking mechanism. So let's watch that again and see how we're powering this on demand. The user wears our wireless power transmitter, which inductively powers the lock and keypad while the user interacts with it. And when the locker opens, we can see that it's been retrofitted with this receiver coil and circuit. This is the key that lets us remove batteries from devices to instead power them on demand. Now, why are we so passionate about this whole business of battery-free devices? Well, by removing batteries from devices, it enables scaling to powering many devices, since we no longer need to maintain batteries per each device. And at the same time, our approach uniquely enables powering across a wide power spectrum and types of touches. In 1991, Mark Weiser famously laid out his vision for ubiquitous computing, where computers are embedded on nearly every object. Of course, all these computers need to be powered somehow, and today we see most small electronics being powered by batteries. This is sufficient for a few devices in a room, but batteries quickly fall short of a scalable solution when we consider that nearly every object will need power, with potentially hundreds of devices and batteries per room, as Weiser envisioned. Now, there has been significant progress in the space of sustainable and intermittent computing, such as Dave Winkle's battery-free Game Boy that harvests ambient energy and energy from user input, and only requires 11.5 𝜇Watts while playing. This is around as much as a single sensor, and under that of a cheap LED. But unfortunately, this approach doesn't directly translate to all devices. And what I mean by this is that there are these devices that need actuators, like motors, that can operate on a very different part of the power spectrum than these low-power chips and displays. They require 10 to 100 times as much power, which unfortunately there just isn't an intermittent schema to power these types of devices. And so the big challenges that we're facing here are, firstly, how can we enable this wide range of devices to be powered, from those that require microwatts to those that require entire watts? And then, how can we enable scaling to many of these high-power devices? And finally, for our touch-based approach, how can we ensure that our approach is robust to different variations of touch? We characterized a few of many related work examples that fall into categories of instrumented environments, body as wire, and encountered type, which each come with their own benefits and trade-offs. Encountered environments add transmitters into the environment for powering devices in their vicinity. These excel at high power like we want for actuation, but they're difficult to scale because there are many environments that just can't be instrumented, such as outdoors. To make wireless power transfer mobile, others have focused on transmitters that can send power directly through the skin. However, the amount of power that we can send through the skin is limited by the current, which unfortunately becomes painful before we can do something like drive a motor. To achieve mobility while potentially powering higher power devices, touch power used a glove instead of the skin. When the glove's power and ground electrodes aligned with receiving electrodes during grasps on objects like TV remotes or clickers, the grasped device could be powered on. While this approach is scalable and high power, it isn't robust to variations in touch, such as unaligned electrodes, single finger interactions, or even hovers. And so, to achieve all three goals of scale, power, and robustness, we built Power on Touch. Our approach is based on resonant inductive coupling, like you might find in your phone charger. However, since our transmitter is wearable, our approach is on demand and instead couples on touch interactions. This comes with its own challenge. Rather than covering what people use to feel the world, we place our coils on the back of the hand and the fingernail. Unfortunately, this comes at a small cost to efficiency. And so, to ensure maximized efficiency over distance and ensure we're receiving high power, we maximize that coupling between the coils by tuning the parallel capacitor's value for each coil. Additionally, each coil has its own natural frequency, where its frequency-dependent efficiency, or Q factor, will be the greatest. Here, you can see plots of Q factor versus efficiency for the many coils that we tested across different geometries. And you can see that each coil has a spike at the frequency where efficiency is maximized. And so, to maximize efficiency, we always tune our coils and their resonant frequencies, and select coils with these high Q factors at resonance. And these steps are precisely what enable us to power this wide range of devices. We made this wearable transmitter that runs off of a small battery, and it pairs up with these custom battery-free receiver tags that feature receiver coils, multiple rectifier circuits, and a supercapacitor for short-term energy storage. Additionally, we include this fast-booting microcontroller to handle logic like when to discharge the supercapacitor through these MOSFETs in order to power actuators and other high-power devices. So let's bring this all together now. When the user touches the small coil, power gets transferred, and we'll see here that the microcontroller boots up, evidenced by the LED coming on. Our tags can convert devices to being battery-free, so let's see how this user converts their digital calipers to being powered on touch using this tag. First, the user removes the battery. Won't be needing that. Then, they solder connections between the tag and the caliper's battery connector. Now when the user touches the calipers, they power on. We performed 5 distinct technical evaluations focused on metrics like efficiency and robustness. Please see our paper for all the fine details. What I'll present here is a small portion of evaluating interacting with a real device. So here is a TV remote that we've retrofitted with a receiver tag, 2 coils, and a vibration motor. We wanted to study how well we could power the remote, both using likely touches and less likely alternative touches, which were informed by the Contact DB dataset. When a button on the remote is pressed, it consumes bursts of power, shown here, with peak consumption around 34 𝜇Watts. We can plot peak power as a threshold of when the remote can turn on, and when we measured the average received power in each of these touch scenarios, we can see that the received power is greater than the threshold in both cases, demonstrating an instance of robustness to different types of touch. Finally, we can plot what happens when a user grabs a completely dead remote in the likely pose. As shown, the supercapacitor charges and the microcontroller boots up in about 2 seconds, followed by the remote being able to send signals. And moreover, we have excess power here, so we can even power up that vibration motor to provide tactile feedback and notifications while the remote is held. We made and tested 9 applications that illustrate our approach. Here's a few. Here, a user wears a coil on their nail to power a service button in a restaurant. As their finger hovers on the button, it powers on and continues harvesting energy, so that when they press it, it can let out that audible chirp and let them know that their table is ready to be served. And since these buttons are battery-free, many can be deployed without charging or maintenance. Finally, this box opens right away when the user grabs it. And of course, there's no battery inside, yet we can still power this motor that takes well over 1 watt. Now, there is a limitation to this work. The user still has to carry a battery and maintain it within their transmitter. And you're probably asking, who is going to want to lug around a battery with them all day long? Well, we all already are. We have things like our phones and our watches and soon-to-be glasses. And the good news is, a lot more people than just me have been thinking about the burden of batteries and coming up with really clever approaches to moving energy around. There's this whole energy economy that's emerging for devices to harvest and exchange energy. And what I'm really excited about is that these approaches all work in conjunction with power on touch, where power on touch can charge its battery through harvesting or sharing power and transfer power back into devices in the environment on demand. Taken all together, this emerging ecosystem points to a future where energy is fluid, battery maintenance is seamless, and with devices like power on touch, actuation can become ubiquitous. Thank you.